Hello folks, my name is Lolachi and today I'm going to talk to you about optical monitoring of the dust environment at lunar surface exploration sites. I work for the University of Maryland, Baltimore County, but I'm based at NASA's Goddard Space Flight Center. I've been working on this project with my colleagues David Glenar and Timothy Stubbs. So why is this research important? With Artemis, we have a new era of human lunar surface exploration coming. The Apollo program showed us that dust is a nuisance and a hazard, being both abrasive and potentially toxic to human health, so it becomes important for us to be able to monitor it. What we know and don't know. We have limited knowledge on how dust is likely to react or move around exploration sites, subject to astronaut activity, rover motion, in situ resource utilization, and the like. However, the dust environment can be monitored by measuring how it scatters sunlight. What would be the resulting brightness of sunlight scattered by an exploration dust cloud? To find out, we conducted the following experiment. We created models of dust light scattering behavior and distribution for irregularly ellipsoid and spherically shaped dust grains. This was combined with a simple dust dynamics model we created. We used these in a radiative transfer model to see what a detector could observe with a modest dust concentration. This was to answer the question, what would a near UV to near infrared camera be able to see? This leads us to our hypothesis. Can off-the-shelf camera optical hardware be used for an exploration site dust monitor? This approach would have advantages over in-situ dust detectors of being sensitive to very small dust grains and providing full site monitoring with a single instrument. And the answer seems to be a resounding yes. Shown here is a brief overview of our method. We started by creating an interpolation grid of scattering properties from the ultraviolet to the near infrared for grains of different shapes and sizes. Then, using a simple dust dynamics model we developed, we modeled the size and spatial distributions for dust grains over an exploration site. Combining the previous elements with the radiative transfer model, we simulated sunlight scattered by dust grains at an exploration site. We could then compare the model dust radiances to the detection thresholds of nominal dust monitoring cameras created with off-the-shelf hardware. We also compared the dust radiances and camera responses to zodiacal light, a source of interference, but also a potential calibration source. Most real lunar dust grains are not spherical, as can be seen from the inset electron micrographs of real lunar dust grains on the left-hand side figure. So, using mean-theory spheres, as is often done, can lead to inaccurate results. We created a grid for visible UV scattering properties, i.e. scattering coefficients and phase functions, for different shaped lunar dust grains. Using the discrete dipole, DDA method, scattering properties were calculated for irregular, prolate spheroid, and spherical grains. The grid extends over a wavelength range of 0.14 to 0.89 microns, covering grain sizes from 0.01 to 100 microns. The left-hand side figure shows dipole positions for our baseline choice, irregular grains. The spheroid shapes we used for comparison. Unfortunately, DDA is computationally expensive, so for larger grains, where the radius is greater than 50 microns, we switched to using the Habke equivalent slab method with diffraction by random Gaussian spheres. Our results were then formatted into interpolation grids using equal log steps. Grain refractive indices are average moon values from Scorato et al. 2009. We now show a preview of some of the grid scattering properties. Starting with the figure on the left, we show the scattering coefficient Q-scat over different size regimes indicated by line style for irregular grains. Effective grain radii range from 0.05 microns to 50 microns. Differences in scattering coefficient due to grain size can be observed. The absorption increases dramatically at short wavelengths, where scattering is less and dominated by the diffraction component. For comparison, we now add lines for the other dust grain shapes, where shape is indicated by line color. Prolate spheres in orange and spheres in blue. Differences in the scattering coefficient due to grain shape can be observed. Next, we present the normalized scattering phase function over different size regimes, again indicated by a line style. Starting in the top right with a plot for different disk grain shapes, a regular prolate sphere and spheres at 530 nanometers, in other words green light, where line colours are as for the left-hand side. It can be seen that smaller scattering angles, in other words forward scattering, are a good diagnostic of size, whereas larger angles, in other words side and back scattering, constrain shape, for the spheroid versus non-spheroid cases in particular. Large radiances can be seen at small scattering angles, but this is too close to the sun for a camera. On the bottom right, we now plot for visible RGB wavelengths at 630 nanometers red light, 530 nanometers green light, and 470 nanometers blue light. This shows variation with wavelength. From the plots on the right-hand side, differences in phase function due to grain size, shape, and wavelength can be observed. The grid was validated against lab measurements of size distribution and scattering phase function for a JSC 1A lunar simulant sample in work conducted by Escobar Cerezo et al. 2018. Here, in the plot on the left, we have results for size measurement and the derived size distribution. The experiment measured the simulant particle size distribution using two different sizer instruments, one that calculated the distribution via a Fraunhofer method and the other by a me-scattering method. These are indicated by the red and blue curves, respectively. The real size distribution lies in between these. So, we derived a log normal distribution, the green line, by fine-tuning the mean grain radius and width so that it was consistent with both the Fraunhofer and me sizer results. Size-weighted scattering predictions for all three candidate distributions were computed using the grid of scattering properties, shown in this plot on the right. The grey diamonds indicate the measured phase function. The resulting angular scattering from the derived distribution demonstrates good overall consistency. In other words, the green line is mostly on top of the grey diamonds. This gives confidence in our method. In order to simulate the sensitivity of a notional commercial off-the-shelf COTS hardware camera, we also need to model dust spatial distribution and abundance across an exploration site, for instance, a lunar surface base. We created a simple ballistic trajectory model for dust launched by activities such as ISRU, astronauts walking, or rover wheels on the surface. This is for a low-density quasi-static, in other words, steady-state dust cloud generated by anthropogenic activity at an exploration site, rather than the short-lived instantaneous high-density clouds created by these processes. This is analogous to the permanent, tenuous, impact-generated exosphere seen by the Lunar Atmosphere and Dust Environment Explorer (LADEE) spacecraft, and represents what astronauts would be exposed to on a chronic rather than acute basis. We start here with our size distribution, governed by the power law seen on the right, controlled by the exponent alpha. For the purposes of this study, we assume a baseline value of alpha equals 0.91, which is consistent with in situ measurements of the lunar ejecta cloud produced by meteoroid impacts seen in LADEE results. However, values are expected in the range of 0.5 to less than 1, with in situ measurements of impact-generated ejecta clouds at the Galilean moons being consistent with alpha equals 0.8. Therefore, we vary alpha between 0.8 and 0.99 to assess the influence of the power law slope on the distribution of dust radii and resulting radiances, as seen in this plot. A key parameter of the dust dynamics model is the most probable speed, UD, which controls the resulting Gaussian speed and velocity distributions. To illustrate its effect, we start with this figure on the left-hand side. This shows speed distributions for values of UD varying between 1 and 10 meters per second. The effect on the scale height is shown on the inset plot. Increasing UD leads to broader distributions with higher scale heights. For this study, UD was set to 2 meters per second. On the right-hand side, we see the effect of varying the most probable speed, UD, on the dust ejection and deposition rates, in other words, the flux, at the surface. We give values for the mass flux on the left axis and the number flux on the right axis. Since all dust is ejected at speeds far below lunar escape velocity, the steady-state ejection and deposition rates are identical. We set a modest value for the mass concentration at the origin, m0, of 1 microgram per meter cubed. For comparison, the instantaneous mass rate of ejected dust from one Apollo lunar roving vehicle is on the order of kilograms per second. So, assuming steady-state concentrations of micrograms per meter cubed is very reasonable. Using this dust dynamics model with a Gaussian velocity distribution, we created a spatial distribution of dust with a peak value of 1 microgram per meter cubed at the origin, as just mentioned. Dust mass concentration scales as Gaussian exponentials in the vertical and horizontal directions from the peak value. The resulting distribution is shown in this figure. On the left, we have a cross-section of the dust mass concentration model across the exploration site. Note the difference in horizontal and vertical scaling of the axes, giving exaggerated corners in contours. On the right, we zoom in to see how the model will be experienced locally. We give the astronaut surveyor lander and Apollo lunar module silhouettes for a size comparison to the vertical scale of the dust model. Because of the large difference between the vertical and horizontal scale lengths, where the horizontal scale length is 100 meters and the vertical scale length is 1.2 meters, astronauts and spacecraft would locally experience an almost plane parallel change in dust abundances. In line with Artemis expectations, our baseline model observation geometry assumes an exploration site near the lunar pole. This schematic shows the observing geometry and mounting of a small and light notional camera aboard a robotic lander. For instance, the polar configuration of Astrobotic's Peregrine lander for NASA's Commercial Lunar Payload Services program. A silhouette of an astronaut is provided for scale. Pink lines show target observation, elevation, and azimuth angles. The target is indicated by the crosshair symbol. Orange lines show elevation and azimuth angles for the Sun. In this coordinate frame, the Sun is at an elevation of theta sun, with azimuth phi equals 0. The horizon is at theta equals 0. The camera is placed 1 meter above the ground. We use this geometry to model an all-sky map of dust radiance due to sunlight scattered by the dust grains. The model abundances can be combined with the radiative transfer forward model and dust scattering grid and used to generate the radiances that will be observed by a notional camera. We can now compare these radiances to the detection limits of a nominal dust monitoring camera in the presence of other background sources, for instance zodiacal light, in order to assess its capability as a dust monitoring instrument. The camera sensitivity model was created from commonly available wide-angle optics and COTS image sensors with flight heritage. We compared the detection limits of several notional cameras using commercial off-the-shelf imaging sensors constructed with wide-field optics, specifications shown on the slide. We used the Shimea sensor used in booster cameras, the Lycia Cube PL1, which is used in the small-sat companion spacecraft on the NASA DART mission to image the impact with the asteroid Dimorphos, and a low-noise but uncooled Hamamatsu CCD sensor with otherwise similar optical parameters to assess the margin of improvement using this device. Shown as dark lines are solar light radiances that produce a threshold detection, in other words, 1 for 1 standard deviation, where the noise equivalent radiance equals 1, for a single 1-second integration for a nominal camera using each of the imaging sensors. These represent ideal detection limits of a dust cam on the lunar surface. Now we add dust radiances from the baseline scenario, irregular dust grains where alpha equals 0.91. Orange traces show spectral intensities from an illuminated dust line of sight of 10 micrograms per meter squared, observed at 2 scattering angles, 30 degrees and 60 degrees, within the camera field of view. The Sun lies at the horizon where theta equals 0. Finally, for comparison, we add the green lines for the zodiacal light background radiance at comparable solar elongation angles. We include zodiacal light here since it's a potential source of interference, but it can also serve as a periodic calibration source to correct for dust deposition on the optics. All 3 conceptual cameras are capable of measuring modest amounts of lofted dust in short integration times. In other words, the black detection thresholds lie below orange dust radiances. Additionally, there is sun sensitivity to zodiacal light, so it could potentially be useful as a periodic calibration source. We can increase the integration time to increase sensitivity to the zodiacal light. We now examine the achievable broadband signal-to-noise ratio for the dust line of sight varying with elevation angle using the conceptual camera with the LiCIA-Q PL1 imager sensor and a 1-second integration. Starting with the dust SNR versus elevation angle, with the sun at 4 degrees above the horizon indicated by the sun symbol on the elevation angle axis. This is for the baseline scenario, irregular grains with alpha equals 0.91. SNR is shown for the dust model path integrated case by the black line, and a case with dust increased by a factor of 10, the black dashed line. The thick dashed grey line represents a 3 sigma measurement above which dust is confidently detected and adequate for constraining the dust size distribution. Note that backscattering from dust may be observable at higher line of sight concentrations. To see the effect of changing alpha, the coefficient controlling the size distribution power law, we add equivalent lines for alpha equals 0.8 in blue and alpha equals 0.99 in orange. Large differences can be easily seen for different values of alpha, so a camera should be able to constrain the size distribution. For comparison, we add green lines showing the SNR from zodiacal light for a camera based at the lunar poles and a camera at low latitudes. For the figure on the right, we again start with our baseline case of irregular grains with alpha equals 0.91, but this time we want to investigate the effect of changing the dust grain shape. Now we add the blue and orange lines which indicate results for the different grain shapes, the prolate spheres and spheres. Relatively large differences can be seen between the irregular and other shapes, the spheroids, at side and backscattering angles. The sphere and prolate spheres are quite similar. They're hard to distinguish from each other. The camera might be able to distinguish between irregular and spheroid dust grain shapes, but the shape distinctions are subtle. More information on shape will be obtained if polarization was also measured. Finally, we add zodiacal light for the same cases as shown in the left-hand side figure. So, sight dust characterization should be achievable using automated, simple, swivel off-the-shelf camera hardware, even for a highly tenuous exploration dust cloud. Dust abundance and effective grain size are readily measurable. Periodic response calibration can be accomplished using constant and bright zodiacal light. Current and future work will include larger grain size DDA models and geometric optics through grid expansion. This will allow the inclusion of polarization effects that will allow greater constraints on shape. We have a manuscript in progress. For the members of the audience that are interested, I give here a list of references for the study. Thank you very much for listening, and goodbye.